Hello, everybody. My name is Deepak Singh. I am the Senior Manager of the Amazon EC2 Container Service, which we announced last year at reInvent. The service is currently in preview, and we've seen a lot of interest in the service. Today, I wanted to cover a number of topics. I wanted to talk about why we built Amazon EC2 Container Service, walk through some of the core features and core capabilities, describe some of the key components of the service, and then we'll actually walk through a couple of examples of how you can use the service. And at the end of it, we may have some time for Q&A and we'll address your questions. So a year or so ago, just after the launch of Docker, which was launched at PyCon in, I believe, March 2013, we started hearing a lot of requests from our customers about native support for Docker on AWS. And that was an interesting question because obviously people had been running containers on EC2 for quite some time. There's a number of well-known large platform services that are built on top of containers and are fairly successful. So we tried to understand why customers were specifically interested in native Docker support on EC2 and what it meant. The first thing that jumped out was that Docker had made running containers, packaging them, and deploying them very easy for developers. And because of that, there was an increased interest in using containers in general, because suddenly containers were not something that were available to a few Linux experts, but in general, developers could use them to build their applications. This was very interesting, and we did a few things to see what people wanted. We made Docker part of the Amazon Linux AMI, and we also launched Docker support in Elastic Beanstalk. And while that was interesting, a lot of what we wanted to do was take a step back and understand what it meant to address this at a much larger scale and much more broadly. The common use cases we were seeing at the time were configuration and deployment. For those of you who are familiar with Docker, this is not that surprising. Docker essentially adds a packaging system around Linux containers, wherein you can have all your dependencies, your application all bundled up together, run them on one system, and then take that same package and run them on another system. And as long as that system could run Docker, you could essentially, and that's the promise of Docker, run that unchanged. So if you're doing a full deployment and configuration pipeline where you're developing on your laptop, maybe you have an intermediate deployment system, and then your final production system, you could keep the same artifacts very consistently throughout the workflow. And so immutable deployments with Docker in particular were becoming very popular, and we saw that quite a bit. The other thing that we were seeing was the adoption of microservices. Now, once again, this is not limited to Docker. Microservices were becoming popular in general because as people were developing newer applications, they were taking those applications, breaking them into smaller components, and then distributing them across a dynamic cluster of instances. It's a very common workflow on EC2, and we're beginning to see even more of that. The good news is that with tools like Docker, doing that becomes a lot easier. Docker provides a natural system in which you want to encapsulate these microservices, these small services, and then deploy them. And so Docker arrived at a time when microservices were becoming popular, and you could say it's a chicken and the egg problem, because Docker, I believe, also made it easier for people to write and deploy microservices. So we were starting to see a lot of that. And last but not the least, we were also seeing a lot of folks doing batch processing. It's not uncommon. This was true even before Docker, to see some of our partners and customers basically encapsulating individual tasks inside Linux containers and distributing these tasks across the cluster to get work done. In fact, some of the common cluster frameworks actually make that a native feature. Docker just made it a lot easier, and the number of people who were trying to do this seemed to be increasing. So these are the common use cases that we were seeing, and as you probably guessed, in most of these, one of the common scenarios is that you are running containers on a fleet of instances. And that was what the problem we decided to set out and solve is, if you have a fleet of instances, which could be a single instance, but typically more, and you're running many containers across them, what's the best way to help you manage them and help you run them? So we started talking to our customers who were doing this already about some of the challenges that they were facing. And we stepped into this wanting to make sure that if we built a service that would make it, we were solving problems that they had, and they could run Docker-based applications on AWS more easily than they could in the past. What are the biggest challenges they were running into? And this was not necessarily just for Docker, but for other container technologies that they may have been running for a while, like LXC or OpenVZ. And there were a few things that jumped out at us as we started talking to them. Notably, uh, they were having challenges scaling their cluster management solutions as the number of instances and the number of containers increased. How they were managing those fleets became a significant challenge because you had to manage the availability of your clusters, you had to manage how your clusters scaled, and how the performance did not deteriorate. So that was one challenge. A sort of related challenge to that was around configuration management. And in fact, this was the one that kept jumping out at us because either the configuration management solutions they were using were brittle, or they didn't know which one to use because there were too many choices. And as they scaled their applications and their fleets, they had to deal with container sprawl because there were just so many containers floating around, often spread out between teams. So they had to manage that. They had to manage the availability of their overall systems and how they're making them available to their internal customers, or if they were offering services to their broader customer base. And as people moved in production and they had either different areas of business logic, scheduling kept becoming an increasing challenge, which was what schedulers should we use? How should we run them? Do we have flexibility in maybe using multiple schedulers, either our own or schedulers that we are using third-party schedulers? And of course, as people moved into production, there was significant concerns around keeping the environment secure, managing isolation, even internally between applications and between teams. So these were the areas that the challenges that people were running into. There are a number of features that people wanted to turbocharge their applications. People wanted integration with elastic load balancing. There's feedback that we got. They wanted integration with Amazon EBS, features like elastic network interfaces, native multi-availability zone support, tagging, identity and access management, security groups. These are just some of the features that we heard about, but as you can guess, or as you can see, people wanted integration into the EC2 and other AWS services that they were very familiar with and comfortable using. And they wanted any native container management solution from AWS to be able to not just address their scalability problems and the, as we call it, the undifferentiated heavy lifting of managing a large fleet of containers, but also access to all the features inside AWS that they liked using. Which basically meant that they wanted containers on AWS to be treated as first-class APIs, much the way we offer a set of primitives for computing today or storage or databases. They wanted a set of primitives that allowed them to run their container-enabled applications easily on AWS. And that is what we decided to build. That is essentially what the Amazon EC2 Container Service vision is, to be a set of first-class APIs that allow you to run applications that are encapsulated in Docker containers. So it is a building block service. We think about it as one. Our assumption is that people will use our APIs to run their applications or to build application services and platforms on top of them. These could be other AWS services. It could be services by our partners or services that you as customers provide internally to your customers. So there's a number of, so our assumption was that it wouldn't just be about running the containers, it would be how you would build on top of them. And that is a core tenet for our service and a core capability we provide. In terms of functionality, we have very advanced state management. The Amazon EC2 Container Service manages the state of your cluster. It gives you all the it tracks all the events that are happening, so any transitions in state that are happening in your cluster, and allows you to query those transitions to figure out whether this is what the current state of your cluster is. The service also tries very hard and does a great job of knowing what your desired state is and making sure that the actual state of your system and the desired state of your system stay in sync. And that is much of the heavy lifting that we do behind the hood. The key is that you do not have any cluster management or state management software to run and install. Everything is a backend service which you access through APIs. Obviously, as the name would suggest, the EC2 container service takes advantage of the state management capabilities to manage your containers. And that is a key part of the functionality that we provide is as you scale your services, the number of containers that you're running, we keep track of what containers you've run, which ones you've stopped, etc. We allow you to schedule containers in multiple ways, and I'll talk about this a little more in a little more detail later. But it's a critical piece of functionality that we provide. And we provide performance at scale. And by this, I mean that as your system scales, as you run more and more containers, our goal is to make sure that the performance of your system, the speed at which your containers get deployed and start running, doesn't get significantly worse. We try and make sure that you can still launch and run containers in a matter of seconds. And that is a big part of what the service does very well at. We obviously wanted to be secure. It was a key area that our customers wanted us to address. So there's a few decisions that we made to support that. One is that these are your containers and your instances. So you are launching a set of EC2 instances and running containers on them. We never allow two different customers, two different accounts to run containers on the same EC2 instance. That's a core feature. And obviously that means that's where you can internally make further isolation decisions based on your internal requirements. And the other part is that you're required to run your clusters inside Amazon VPC. So you can benefit from all the network isolation capabilities that VPC provides. And these are features that many of our customers are very familiar with, and they can continue to take advantage of. And we wanted the service to be extensible. As I said earlier, our goal was to build a building block service which people would use as a starting point to build more high-level platforms. So you can take our APIs, you can extend them. I'll talk a little bit about our agent in a bit. You can extend our agent. And of course, you can do a lot of interesting things with scheduling, including writing your own schedulers, something else we will talk about shortly. So what are the key components of the service? There are 4 key components that we like talking about: tasks, containers, clusters, and container instances. Let's actually start from the bottom and container instances. A container instance is an Amazon EC2 instance, which has a couple of key requirements. It needs to be running the Docker daemon that we support. Currently, we support everything from Docker 1.3.3 and above. And it needs to be running the Amazon ECS agent. Obviously, it needs to run a version of Linux which will support Docker, which is any modern version of Linux kernel should do the trick. We provide an army, an Amazon Linux army that meets these criteria, but you can use another operating system as well. In fact, CoreOS supports EC2 container service natively right now, and our other partners are adding support as well. The Amazon EC2 container service agent, the ECS container agent, is a piece of Go code that we have open sourced. You can find it on GitHub in the repository listed here. And it's licensed under an Apache license. We also make it available as a container from Docker Hub. And in fact, if you look at the Amazon Linux army, you'll notice that our agent actually runs as a Docker container itself. This agent is what tracks the state of your container instances and makes the service aware of the state of your containers. Essentially, once the agent is checked into a cluster, it is that instance is available for our service to manage. And that is so it's a critical component that you need to have running. The next critical component is the cluster. Clusters are made up of container instances. They are regional, so a cluster spans availability zones. And they essentially provide a resource pool of CPU and memory and network capacity that your containers can use for whatever you want to run inside those containers. Clusters are an abstraction. They start empty and they're dynamically scalable. You can add and remove instances from them. The key thing to note is that clusters do not require heterogeneity. You don't have to have container instances of the same type in your cluster. You can have a mix of instances. You can have C3 instances. You can have R3 instances as required for your applications. And they are provided as one big pool, which you can launch into. One of the most important units or components inside EC2 container service is the task. The task is the main unit of work inside the service. It is what is used for scheduling. Essentially, a task is a grouping of related containers or a set of containers that you want to use as a minimal scheduling unit. You essentially launch a task onto container instances. And if there's not enough resources on the container instance, your task gets rejected. That's a critical unit of scheduling. Your task can consist of a single container if you want, but typically we see tasks with more than one container on them. Here's an example of a task being defined via what we call task definitions. In this case, you have two containers in this task definition. The first, this is WordPress if you haven't guessed by now. The first container is running WordPress. You give the container a name, you define the image that you're pulling. In this case, these are images being pulled from Docker Hub. You define the minimum CPU that's required. You assign memory. You define if the container is true, is essential or not, which means that if the container dies, then the whole task dies because the container is essential. And then you also can describe links in addition to any network ports that you're defining. A link is another container on the same instance that is linked to this particular container. In this particular case, we have a container called MySQL, which is linked to our container called WordPress. And as you notice, there's no networking defined for the MySQL container. It essentially talks to the world only through the WordPress container, which has host port 80 and container port 80 assigned. This is for the web server, of course. But this is an example of a task definition. You can build somewhat complex task definitions for if you have many different services that you want to schedule together onto a common host. So here's a typical workflow that a user might use. There's others as well, but this is not uncommon. You may have a Docker image, and you may want to run that image on a cluster. So you push that image to a Docker repository. In this case, we've pushed it to Docker Hub. You then want to create a task definition and register it against the service. The task definition essentially declares your resource requirements. You want to launch a cluster of EC2 instances and with our agent and check them into a cluster. In this case, we've just decided to check them into a default cluster, which everyone has access to. We then describe our cluster, and as you can see, you can use list or describe or a combination of those. You have a VPC with 3 container instances and nothing running on them except the Docker daemon and the Amazon ECS agent. You can then run task. Run task is an API that randomly schedules containers or essentially tasks onto your fleet. In this case, our task consists of a single container. And as you can see, if you do describe cluster again, our scheduler has scheduled one task each or one container each, in this case, on each host. So this is a fairly simple example, but it's not unlike a lot of other scenarios that you will see on using the service. There are 3 ways to start a task, and actually this is a sort of somewhat unique to our service and something we wanted to give our customers, which is you can use the start task API to target a specific container instance. In other words, you can basically say task definition X should be launched on this particular container instance. Hopefully there is enough resources on that instance. If they're not, the task gets rejected. Otherwise, it starts running on that. You can actually give a list of instances. So if you want many copies of that task running, you can actually run it on multiple instances. That is one way of launching containers onto your fleet. The most common way of doing so is likely going to be using our run task API. The run task API randomly schedules containers across the fleet. So in this particular case, you see an example of a single sleep 360, which is just a simple sleep task, being launched onto our cluster. Count could be 100, and depending on the size of your cluster, this API call will try and schedule 100 copies of this task definition onto your cluster, and as long as resources are available, they'll get scheduled. And it's a randomization approach. It tries to balance availability with trying to prevent a single instance, for example, from getting every single task being launched onto it. You can actually take our list and describe APIs and the start task API and build your own scheduler and integrate into existing schedulers as well. For example, you can use a Mesos scheduler like Marathon or Kronos with some modifications to the scheduler drivers. You can actually use those schedulers with the Amazon EC2 container service. And you'll see an example of that in a few minutes. Or you could write your own business logic or multiple schedulers with different business logic to use our APIs and our state to decide how you want to launch new tasks for your organization. So you can target specific container instances. You can use our random scheduler where you don't need to make any specific scheduling decisions, or you could write your own or bring in a third-party scheduler. We allow you to do it all any which way you want, or mix and match any of these options. So let's take a look at how the service works. At this point, I am going to jump into a shell, and hopefully you will can see it. So let's start off by listing all the clusters available to me. And I'm going to use the Amazon Web Services CLI that I suspect most of you are very familiar with. And if you're not, there is extensive documentation for how you can install it. I would like to note that at this point of time, the container service does not have a management console. So you have to use the AWS CLI or our SDKs if you want to integrate with them. Or as you will see, you can use third-party tools to do so as well. So let's list all the clusters that we have. As you can see, we have two clusters running. Our default cluster, everyone gets a default cluster. And we have a scheduler called OMG, which I am not going to even try and see what is happening inside it. The next thing you might want to do is list all the container instances that are part of this cluster. And I suspect you're getting very familiar with how the verbs in our API. You always are needed. You always have to describe the cluster. Outside of the cluster, all the API calls are in the context of a cluster. So containers, instances, tasks, everything requires a cluster. And voila, we have a cluster with 5 container instances in it. At this point, you might want to list all the available task definitions that you can use that you can launch onto this cluster. So let's list those. So we have a few task definitions available to us. This would be a good point to actually talk about how you register task definitions. When you register a task definition, you actually give it a family name. And if you register a new version of that specific task definition, it actually does not overwrite the existing task definition. It actually versions it. So as you can see, we have 2 versions of Nginx, 2 versions of Sleep 360, and 1 version of WordPress. At this point, you might want to run a task. So let's try and run a task, Sleep 360, for example. That's the easiest one to run. And so let's do that. Oh, actually, before we do that, why don't we list the tasks that are actually running? So let's do that. AWS, using the same sort of way of similar terminology here, we have to list our cluster. As you can see, there's a couple of tasks running. Let's check out, copy this, and we can actually take a deeper look into the task, which is, this is a bit of a longish command line call, but bear with me. And as you can see from the JSON, this is the UUID of your task. It's a task named Nginx. Its last status is running. The desired status is running. So as I said earlier, the backend tries very hard to keep your desired status and the actual status in sync. And we actually let you know what those are. You come to know what container instance you're running on. You might want to take a look at that. if you wanted to get more information about a container instance. And as you can see, if I'll scroll up a bit, here you come to know that this container instance is active. You find out a little bit about the registered resources. So, for example, you have CPU resources with a value of 1024, and 1024 is an arbitrary number. We call it 1024 CPU shares, and that is how many CPU shares are available if you have one core. It tells you what the instance ID is, so you can look at it in greater detail in your Amazon EC2 dashboard. It tells you that the agent is connected. It tells you what resources are available for you to run jobs on. So as you can see, using our list and describe APIs, they're pretty powerful, and they tell you a lot about the clusters, the container instances, and the tasks that you're running. And at the end of it, why don't we just run something? So we're going to run a sleep 360 task. It is one of the task definitions available to us. And we will use our run task API, which will randomly schedule this task for us. And we are going to run 360 and version 2, which is the latest version of this, on our default cluster. And it's launched. So if we again go and list our tasks, and I'm just going to go back and look at them, we should have a third task running, and we do. So this was using the AWS CLI. You can obviously integrate with all our SDKs, support the service as well, which is how I suspect many of you might use them. But I promised earlier that you could use a third-party scheduler with the container service as well. So I'd like to demonstrate how you can use Marathon and Kronos, which are two very well-known Mesos schedulers, with EC2 container service. The way we have done this, and I'm just moving over to my browser where you can see Marathon. For those of you who are unfamiliar with Marathon, it is a scheduler for the Mesos framework. It allows you to run long-running services. And the way we've integrated Marathon with EC2 container service is by writing a Mesos scheduler driver. So there's no Mesos master or Mesos slave involved. Marathon is talking directly to the EC2 container service backend. If you remember, we had an Nginx task running. That's what you can see running here. Let's click on this task, and there you have some more information. It's giving you the ARN of the task and sort of the container instance that it's running on, and you get that information. Why don't we scale this? Right now, there's only one copy. We wanted to run 5 versions of this task. So we do that. And as you're looking at it, you can see that Marathon will now take it from 1 copy to 5 copies of Nginx. And if you go back here and run list tasks again, you will see a lot more tasks than we had earlier running previously. These are all the new tasks that we just launched. Let's go back to Marathon and scale this back to a single task. And it takes a few seconds for the call to register, and voila, we're back to running a single task. If we go back to our list tasks call, you now have a single task running. You'll ask what happened to the sleep task that was there earlier. Sleep task, it runs for 30 seconds and then runs every 1 minute. So it'll come and go. So if I redo it now, you may see a second task show up. There we go. And it's just a task that keeps getting scheduled onto the cluster as resources are available. Now, the Mesos ecosystem has another system called Kronos. Kronos is meant for launching batch jobs, and a sleep task is the cheapest batch job I can show you because it doesn't take up too many resources and it runs pretty quickly. I already have a sleep task running, and as you can see, that's the one that you see coming and going. It's actually run 5,769 times. because I launched it a few days ago and it keeps launching every minute. Let's run another sleep task. So let's close this one and run a new job. And let's call it sleep job number 2. And the command will be sleep 360. Let's run that again. And we want it to update every 1 minute. So Marathon allows you to do that. Let's schedule it for, these all in UTC. So hopefully that time is right. And we hit create. Oh, it wants me to give an owner. Sometimes it does, and sometimes it doesn't. So I'm just going to enter a random owner, if you don't mind. And click that. So now we have 2 jobs, and you can see there's 2 jobs. One has been running successfully. The other one is going to get scheduled shortly. We can come back to it. But back, I won't do this to you. You can keep running list tasks every few seconds, and you'll see which jobs come in. Now let's actually take a look at, keep an eye on our sleep job number 2. And in the interest of time, I'm actually going to force run it. That'll just run that job, and you will see the fresh turn to a success over here. And if I go here, you can see that it just, because I force ran it, it actually just started. And if you come back here, you should see a success roughly 30 seconds after the job runs. You will see a success basically saying, hey, I have now run the first iteration of the sleep task. And it'll keep running because I've told it to run every minute. And we can keep looking at the screen. And hopefully any time now, this status should be changing from fresh to success. And seconds sometimes take much longer than you think they should. Actually, while we are at it, let me run list tasks again, see if there's actually 3 tasks running. No, okay, it's run. And that should be changing any second now. That's what we call demos not collaborating with you. It might have been the other sleep task that actually ran because that was running on its own, then this one was being force run. Okay, that might be the task that we were looking for, because there we go. As you can see, the task is now a success. And if you go back here, you should have back to having 1 task running. So we have 2 tasks, sleep tasks being scheduled onto our cluster. We have an Nginx task running. And as you can use our list and describe APIs to see what's happening on the cluster. The point was that you can integrate any third-party scheduler with EC2 Container Service. So if you are using Marathon or Kronos or Singularity or Aurora, another Mesa scheduler, it's relatively simple integrating it with our service. I briefly alluded to a scheduler driver earlier. It's something that we plan to open source very shortly. And hopefully that will give you a starting point for your own integrations. So let's get back to our presentation here. Hopefully you got a little glimpse into how you can use the AWS CLI or a third-party scheduler with the container service. The service is currently available in preview in 1 region, which is US East, and at no additional charge. So if you pay for the EC2 instances that you're using, or if you're using any EBS volumes, or if you choose to put your images in Amazon S3, you will pay for other AWS resources that you're using, but the service by itself has no additional charge. And we are just getting started. We've received excellent feedback from our community in the AWS user forums, via email, by people contacting their account managers. I would encourage everyone to do the same. We've provided a core set of building blocks. We would definitely like to expand on that, and the way we do so is by taking feedback. So please don't be shy, and thank you very much.